Gamma-ray bursts. Gamma-ray bursts are the brightest known explosions since the Big Bang, releasing as much energy in seconds as the Sun will emit over its entire 10 billion year life. They come in two main types: long GRBs, lasting more than 2 seconds, produced by the collapse of a massive, rapidly spinning star into a black hole, and short GRBs, less than 2 seconds, produced by mergers of neutron stars, or a neutron star, and a black hole. In both cases, a newly formed compact object drives ultra-relativistic jets, narrow beams of particles and radiation moving at greater than 99.9% the speed of light. Because GRB energy is beamed, the actual energy is funneled into jets, typically only a few degrees wide. If one of those jets is pointed at a planet, the prompt emission arrives first, followed by a multi-wavelength afterglow as the jet shocks the surrounding gas. The beaming means most GRBs are harmless to us, but it also means the few that are aligned can be catastrophically intense. The lethality mechanism is atmospheric chemistry, not fireballs. A gamma-ray burst within a few thousand light-years aimed directly at Earth could strip ozone by producing nitrogen oxides in the stratosphere. With the ozone layer depleted, the Sun's ultraviolet radiation would spike at the surface for months to years, damaging DNA, collapsing food webs, and triggering mass extinction-scale ecological stress. Supernovas. A supernova is the final, explosive stage in the life of certain stars, and it is among the most violent processes in the universe. The physics differs depending on type, but the outcome is always the same: an enormous release of energy in a very short time. In a Type 2 supernova, a massive star runs out of nuclear fuel. Without fusion to provide outward pressure, gravity takes over, causing the core to collapse into a neutron star or black hole. The collapse rebounds, sending the star's outer layers hurtling into space at up to 10% of the speed of light. In a Type 1 supernova, the trigger is a white dwarf that pulls matter from a companion star. Once it crosses a critical mass limit, carbon fusion ignites uncontrollably, tearing the star apart completely. Both events release energy comparable to the Sun's entire output over billions of years, compressed into weeks. The radiation from a supernova at less than 30 light-years could strip Earth's ozone layer, while the blast of high-energy particles would reach the solar system centuries later, bathing the planet in ionizing radiation. The geological record holds evidence that past nearby supernovae left behind iron-60 isotopes in Earth's crust and ocean floors, suggesting they may have contributed to extinction-level ecological disruptions. A supernova is rare on human timescales, but astronomers estimate one occurs somewhere in the Milky Way roughly every 50 years. Magnetars. Magnetars are neutron stars taken to an extreme. Their magnetic fields are 1,000 times stronger than that of an ordinary neutron star. A magnetar's field is strong enough to distort atomic structures. Within a few hundred kilometers, it could literally pull atoms apart by overwhelming the electromagnetic forces that bind electrons to nuclei. The most dangerous feature of magnetars, however, are their starquakes. When the magnetic field twists and fractures the crust, it releases an enormous burst of energy. Gamma-ray flares so intense they can be detected across galaxies. In 2004, a giant flare from magnetar SGR 180620, located 50,000 light-years away, briefly altered Earth's upper atmosphere. If such an event occurred within 10 light-years, it could strip ozone, irradiate the surface, and destabilize ecosystems for decades. Although magnetars are rare, just a few dozen are known in the Milky Way, the sheer magnitude of their outbursts makes them one of the most dangerous compact objects in the universe. Black holes. Black holes are formed when matter is compressed beyond the point where even light cannot escape. Their lethal effects come from 3 different mechanisms: gravity, radiation, and motion. First, the gravitational field near the event horizon creates tidal forces so strong that objects are stretched into thin streams, a process known as spaghettification. Second, when gas or dust falls toward a black hole, It forms an accretion disk. Friction heats the disk to millions of degrees, causing it to emit X-rays and gamma rays powerful enough to sterilize star systems nearby. Third, black holes can launch relativistic jets that extend thousands of light years, blasting high-energy particles into surrounding space. The danger is not limited to those at galaxy centers. A rogue stellar mass black hole drifting through the Milky Way could destabilize entire planetary systems. Its gravity could shift orbits, eject planets, or pull comets inward, increasing impact risks. Fortunately, most known black holes are located far away. The nearest candidate is about 1,500 light-years distant. Still, because black holes are invisible unless feeding, astronomers believe many more remain undetected. The potential for disruption makes them an ongoing cosmic hazard. Quasars. Quasars are the visible signature of supermassive black holes actively consuming matter. They are the most luminous, persistent objects in the universe, outshining entire galaxies. The accretion disks surrounding these black holes generate light across the entire electromagnetic spectrum, from radio waves to high-energy gamma rays. Jets of particles shoot out at nearly the speed of light, extending hundreds of thousands of light years. The destructive power of quasars comes from their sheer radiation output. A planet inside the beam of a quasar jet would experience radiation so intense that its atmosphere would be stripped away in a short time. Even at distances of thousands of light years, the ultraviolet and X-ray output could erode planetary atmospheres and prevent complex life from emerging. Quasars were common in the early universe, when galaxies were young and gas was plentiful. Today, the Milky Way's central black hole is relatively quiet, but if it were to reignite into a quasar, the consequences for life across the galaxy would be catastrophic. Hypernovas. Hypernovas are among the most extreme stellar deaths, linked to stars more than 30 times the mass of the Sun. They are thought to be the origin of many long-duration gamma-ray bursts. Unlike a standard supernova, which blasts energy roughly evenly in all directions, a hypernova channels much of its energy into powerful jets, moving at nearly the speed of light. These jets are what make them especially deadly. When a hypernova occurs, the combination of the explosion's total energy and the concentrated radiation in its jets means its destructive radius can extend thousands of light years. If aimed at Earth, such an event would not only strip away ozone but also bombard the surface with enough ionizing radiation to sterilize ecosystems. Hypernovas are relatively rare compared to standard supernova, but their link to gamma-ray bursts makes them one of the most credible candidates for triggering past mass extinctions on Earth or other planets. Rogue stars. The galaxy is not a stable, orderly place. Gravitational interactions between stars often eject planets or even entire stars, sending them drifting through interstellar space as rogues. A rogue star passing within a few light years of our solar system could gravitationally disturb the Oort cloud, sending a rain of comets toward Earth. A closer encounter could destabilize planetary orbits, making Earth either too hot or too cold to sustain life. Rogue planets, while smaller, carry their own risks. Though dark and difficult to detect, they can still collide with other planets if paths intersect. Even a planet the size of Mars, if on a collision course with Earth, would annihilate the biosphere. Simulations suggest the Milky Way contains more rogue planets than stars, possibly in the hundreds of billions. While the probability of a direct encounter is low, the sheer number makes them one of the more persistent long-term hazards. Cosmic rays. Cosmic rays are atomic nuclei accelerated to near light speed by violent astrophysical processes. They constantly bombard Earth, but our magnetic field and atmosphere absorb most of them, making the background level tolerable. The danger comes when something dramatically increases their intensity, such as a nearby supernova, gamma-ray burst, or an active black hole jet. When high-energy cosmic rays hit Earth's atmosphere, they generate cascades of secondary particles. Some, like muons, can penetrate hundreds of meters underground or underwater, meaning no part of the biosphere is completely safe. At elevated levels, This radiation damages DNA, causes mutations, and raises cancer risks. On geologic timescales, spikes in cosmic ray flux may have contributed to extinctions. If Earth were exposed to a sudden surge, it could overwhelm natural shielding and leave the surface uninhabitable. Cosmic rays are less dramatic than explosions or black holes, but their persistent, cumulative damage makes them one of the deadliest cosmic phenomena.